Oh, microphone's on. Cool. Hi, everyone. Welcome in. My name is Penn Center. We're getting fired up for our first lecture series in real analysis, which is super exciting. Oh my gosh, the yellow lights are still here from last night. Dang, the yellow lights. That's bright. Oh. Alright, let's get the ad roll out of the way. Ads incoming.
Time for a pop quiz.
Good luck and snag a QED point. Yeah, who else is on today? Just high potential right now. Wait, I think Dawn's supposed to pop on this afternoon as well. But yeah, we all be assembling. We're getting ready to go for our introduction to real analysis. So we're going to be talking a little bit kind of about the expectations today, a little bit about just some basics for set theory. McKenna's going to take care of that. And then I have a little kind of introduction to logic and proofs for those that really haven't done some work in logic and proofs before. The first main presentation for real analysis will be next Saturday at 10 a.m. Pacific time. Or sorry, next Sunday at 10 a.m. Pacific time. So that's going to be on January the 26th. And that's going to be by Sir Dingus. Great, fantastic Discord username, by the way. Fantastic. So I'm going to have to fire off music here. We will just set that to pause for now. And we're going to have to fire down StreamerBot as well, so we don't get any of those. Boom, let's do that. So we get no pop-ups when we get people popping in, and we don't want any of that going off to YouTube. So for those of you that are watching the video on demand, this is kind of the typical style. So we'll have our presenters come in, they kind of talk for about 1 to 2 hours or so on the selected topic. I'll be recording things via Twitch, and then we basically export that video over to YouTube. And once we do that, we provide you with the link so that you can catch up and take a look at that video afterwards. All right, we're just about back. We've got about 30 seconds left in the ad roll, and we'll pop back into the Discord server and see what's going on. All right, we are back. Things are looking good over on the Twitch side. Yeah, Darp. So when I host the presentations, typically I live stream them to Twitch at the same time so that different communities can kind of find us and jump in. And that's it. Then we can export the video to YouTube as well. So after everything's all said and done, we'll export that video over to YouTube and post it for people that might be on the other side of the world and can't necessarily join in. Yov or Aha, would you mind throwing a lectures ping into the announcements and let folks know that we're just about to start? Awesome. Thanks, Yov. Much appreciated. Hi, Zach. Welcome into Twitch chat. I did turn off the alert, so I'll give you your QED point later. I'll give you your QED point during the bonus math stream today. Is that you, McKenna? There's 3 of you now. Euler, are you talking about audio on Twitch or audio here in Discord? I'm hoping audio in Discord's okay.
I had to watch your Twitch to know you're saying.
So what I'm doing is I'm porting. So I use OBS. So I'm porting virtual camera from OBS into Discord. So if you're trying to follow my mouth, it might not line up perfectly. It really probably should just say set basics. We're just doing some introduction to set things.
That thing.
Set things.
Wait,
Things about sets.
you love that.
No, today's presentation
No,
is
it's
not
not.
about the axiom of choice. We'll probably talk about the axiom of choice a little bit next week.
Oh.
Oh my gosh, we're
Wasn't
getting.
axiom choice like you can pick either different types of number systems to the or sorry, no, you can pick different axioms to define something. Man, I'm getting rusty on the real analysis.
Axiom of choice? That just says that like if you have an
Yeah, well,
an infinite collection of non-empty sets, you can pick an element from each set.
I see. I got the analysis book.
Oh damn! Is that a bot?
Yeah, the bowl.
Oh Darp, that's a Twitch functionality. Thank you Zone Ranger for the Prime subscription. Much appreciated, my friend.
I should clean the room.
Hi Fem, welcome in. We're just about to get started. Grab a snack, grab a coffee. I don't even know why I'm here. I can't even do proper school math. Well, I mean, I'm hoping that the first couple introductory lessons are going to help you build a little bit of that foundation. I'm here because I'm bored. For a lot of you that have taken these mathematics classes, these are coming in at like not a crazy high level. So don't be expecting to like any freaking like metric spaces or anything like that happening today.
Yeah, we're not gonna get into your Lebesgue measures.
None of that's happening today. It's gonna be pretty chill.
Sadly not. No, not the Principia Mathematica. We're not gonna spend 400 pages on 1 plus 1 equals 2.
I have a copy of Principia Mathematica in my office. I could always bring it in.
Oh, really? Yeah, I read like a page of it and then like, oh wow, very cool vocabulary. Let me use this. I sound like a nerd. Dogmatic beliefs.
Yeah, I have Newton's Principia.
Oh, you have Newton's Principia. You know, there's another one by these two authors. I forgot their names. Uh,
All right, I think we are just about ready. I'm going to grab a link here. So, McKenna, if you're cool, what I'll do is I'll just kind of introduce everything and then kind of set the expectations for the reading group. I'll give you an opportunity to add in anything that you want after I'm done with those first introductory slides, and then I'll pass over the presentation to you. And then you can just let me know when you want me to bounce over into the Excala draw page, if that's cool.
okay, yeah, that would be great.
Sweet. So welcome in, everyone. My name's Penn Center. We're joined also with McKenna, and we are super excited to start up the Real Analysis Reading Group. So this particular presentation, which will be about 1 to 2 hours long, is just kind of setting up some of the expectations for the students, for the presenters, what that's going to look like. McKenna's going to talk a little bit about some set basics, some of the operations that might be helpful for you to know before we start moving into some of the analysis stuff. And then I'm going to talk a little bit about more of the logic and proof stuff, kind of specifically taking a look at quantifiers and how we want to structure proofs with quantifiers and structure proofs with sets as well. So there's a little bit of an overview here. I want to talk first a little bit about the expectations. Then I'll hand things over to McKenna for some of the set basics, and then I'll take the floor again once we get to the logic and proofs section. So for those of you that just got the ping and you don't know about the reading group, please head over to, I'm just going to post it into the chat. So head over to the announcements inside the math server, and you can go ahead and react to, just scroll up a little bit, you can react to the announcement about the Real Analysis Reading Group. So if you're interested in attending, like maybe you're a keen high school student or just kind of finished calculus as an undergrad and want to learn a little bit more about why some of these foundational things work in mathematics, then I would say react with the book emoji to that announcement. And then that'll give you access to the channels. Specifically with regards to when the presentations are happening, they're happening on the weekends. That was voted upon for those of you that are in the reading group. Time is usually dependent on the presenters. So for example, like next week it'll be Sunday morning. So if you're a presenter and we need to work a little bit around your schedule, that's cool with me. So we kind of meet on Saturdays and Sundays. We'll do a presentation style kind of like this. We usually live stream that over on Twitch as well so that we can save a recording. I'll post up some recommended reading from some of the resources that we have during the week. You can take a look at some of that recommended reading, and then that way you have a capacity to bring in some questions if you want during the presentation times. Usually, like I said, about 1.5 to 2 hours is usually pretty standard, and then we'll post up that video if you're unable to attend afterwards. After the presentation is done, we'll go through some of those resources that we've posted up and try to maybe grab a small selection of questions, and we'll try to post them up into the forum. So we have 2 forums, one for the real analysis part and one for kind of Talos's calculus class that's happening simultaneously as well. For those of you that are here that have already taken a course or several courses in real analysis, if you're interested in presenting, you can go into the announcements on the math server and just click on the teacher emoji. And that way you have access to all of the channels in the real analysis category, as well as the presenter channel. And that's where we'll do some of our planning inside that group chat. So what we usually do for presenters is I'll try to make like a call or 2 calls, and I'll try to list out the topics that we need presenters for. And so if you're looking at something and you're like, oh yeah, I could make a presentation about that topic, just let me know. So for example, this isn't updated because Coffee is working on continuity, but we're still looking for someone to cover monotone convergence, Bolzano-Weierstrass, and discussion about Cauchy sequences. So if you're interested in making a presentation about that, let me know, and we can start working out some of those arrangements. So lots of references. So we have lots of textbooks that we can provide for you, or sections of textbooks if you're interested in doing that. And then the format's totally up to you. So today we decided to make a Beamer presentation, but some people might want to do like a more kind of traditional style, like writing on a piece of paper I've seen, or like using Excalidraw or OneNote or something like that. So it's kind of open to how you want to present things. Cool. Yeah, is there any questions kind of about the expectations? Feel free to let us know in the chat. You're also welcome to raise your hand to ask your question as well. Oh, sorry, Sensation. I think show's off today. Show's taking the morning off. Zach is wondering, will this be on the test? Yes. And yeah, I see McKenna's fielding some questions. So yeah, if you've taken a course in real analysis and you're just interested in kind of brushing up those skills, that's probably all we need for the presentations here. Of course, if you've taken some more courses in real analysis and you want to add a little bit more beef, I know that Coffee, for example, is going to add a little bit more content to the functional limits and continuity chapters because they're really interested in doing that. You're welcome to do that as well. So that's a good question. What is real analysis about? So I would argue, or at least venture a guess, that real analysis feels to me kind of like that foundational course that most students would take after their Calc 1, Calc 2. So after you've kind of learned a little bit about integration, differentiation, and some of those properties, then typically for a pure math student, you kind of transition into real analysis and start kind of following that path and see where it goes. So it's kind of like the next step, and we go back and we try to really rigorously define some of the concepts you see in calculus and provide, I think, more rigorous proof than what you normally would see in a first-year calculus class. Yeah, so no sign is saying the same, right? So we do a little bit of analysis of like sequences and series, and then we try to kind of take some of those fundamentals that we have and apply them into functions as well. So we do kind of some functional limits and properties of that as well. Cool. So I'm going to go ahead and I will toss the floor over to you, McKenna, to start chatting a little bit about some of the kind of basic set theory stuff that students might be helpful for them to know, kind of moving into some of the next presentations.
Okay. Yeah. Right. So, with set theory, if you haven't like seen any of the notation, this is some of the basic notation. The first symbol we have, which looks like I guess like a weird looking E. It's you can think of it like if like the elements of whatever you're putting is contained within some other set. Is there a way for me to write something? Like,
Yeah, so if you want me to kind of bounce over into the Excalibur draw, just let me know.
Yeah, sure. That'd be great.
And then are you able to port any pictures over into there that you'll need?
Yeah. Okay.
Okay, sweet.
Oops. Okay. So let's say we have some set A, and then we say in set B. This means that our elements in A are also in B. The second symbol we have is called a union. So the basics of a union are if we have some set, let's say A, and then we have the union of that and B, then that means that that set, the combined set, is both those sets combined. Maybe you've heard from algebra class, maybe you could say that the real set is equal to the rationals and the rationals.
McKenna, may I?
Yeah, sure.
Darp was just wondering about our in symbol. Are you able to expand a little bit on that, Darp?
Yeah, sure. So the in symbol, right? Let's say you have some set n, and n is some inside the naturals. So you could say that n is contained within inside the rationals, and all the elements of the naturals are inside n. A way we can use this is, say we have some set, maybe some series, right? And then we could say that this, let's say the index is any set or any number n. So n is your natural number. So 0, 1, 2, 7. Right. Are they questioning what a subset and the difference between the in function and a subset?
Yeah, I think they were just like looking for us to provide some clarification, which I think you did here.
Right.
So like if there's an element, we usually use the in and then
yeah. If it's in, it means it contains all of the elements, while a subset is just a portion of some of the elements. If that makes sense. Okay. And then we say the next symbol, or should I go over units again? Or
Sorry, go over which again?
should I go over unions again? So, union. Okay, so uh, a union combines two sets together. So we could say the real numbers is equal to the union between the rationals and rationals, because the real set is just these two combined. And then an intersection is the element of a set that both sets share. I'm not sure of an example of that, but I have some stuff on the next slide about unions, or it was on subsets, but yeah. And then we have some basics of cardinality. Cardinality is, in essence, how much stuff is in a set. And the way we use cardinality differently from just seeing how many elements are in a set is cardinality specifies more further on uncountable sets or sets with infinite elements, and it allows us to give somewhat of a measure of how big an infinite set is compared to other infinite sets. And then our basic function notation. F, we say a function f maps A to B. We can see this in regular math as this f of A equals B.
Shit.
Wait, can I actually write onion? Oh, I did write onion. Oops. Okay, let me go to the next slide. This next slide is about sets and subsets.
It'll take me a second to boot that back up. My laptop died.
Yeah, I saw.
Yeah. Like of all the times for my laptop to not actually be plugged in.
Oh no. No, yeah, it's everyone. Everyone can't see the screen. Sadly.
See you, Darth. Classic.
Yeah.
Twitch chat knows. It's like this is a classic Pen Center, classic Pen Center thing.
Oh really?
Technology like hates me wherever I go.
Oh wow, we're logging back in.
Oh yeah, we're like straight up booting the laptop up. Just notice how dapper McKenna is? Totally.
Dang.
Okay, let's pop the slides up and then I'll get back into Excalibur here too. Don't look at me, I don't torrent anything.
It is not my common for it, sadly. I do not have a $4 ownership.
I'm tired of everyone treating me like I'm a child. I'm older than 13. I eat unhappy meals now.
Hi, DZ, how are you? Do-do-do-do. All right, next slide.
Okay, next slide. What is a set? A set is a collection of objects called elements, and we write them down using the notation as shown, which is usually using the curly brackets, and then your elements listed. It doesn't have to be I subscript 1, I subscript 2. Usually we put like, naturals is curly bracket 1, 2, 3, etc. And then some other sets that we use in a lot in real analysis are the real numbers, the integers, and the naturals. And then we talk about what is a subset. A subset, I say, like some people confuse the in symbol with a subset. So the in symbol means that all of the elements in a set are contained in the other set. And then a subset is a portion of some of the elements in a set. So we can say like the naturals is a subset of the reals because it only has some of the elements of the real numbers. Yeah, thanks. The naturals is a subset of the reals because some of the elements in the naturals are contained in reals, but not all of them, because the reals is a much bigger set than the naturals. Okay, can you, actually, I'll just pull up the next slide in extra chart.
Yeah, sure.
So we come to the notion of what is a proper subset. The problem with the normal subset is that a subset can be equal to the normal set. So we can say like, what if naturals is a proper subset of naturals? Well, that's pretty, I guess, trivial to say. And we could also just said, well, it's also just this, which kind of defeats the point of a subset if they're just equal. So we come to the notion of a proper subset. A proper subset is a set or a subset that does not contain all of the numbers, only contains a portion of the numbers. So we could also write the statement previously as naturals is a subset of the reals, or a proper subset specifically, because it contains not all of the elements, but some of the elements. And then our next slide is about some of the advanced method notations. So these are some of the most common notations we use in analysis with sets, of course. We call it real analysis because we study real numbers. But before we do that, we like to talk about sequences. Sequences use natural numbers, of course. Integers we use because sometimes we want natural numbers, but if we had them in the negatives, and sometimes excluding zero, sometimes excluding zero. Irrational numbers helps us define fractions or division. And then the real numbers gives us wholeness or completeness in analysis, which is a property you'll learn later about. And it's a pretty important property and allows us to say different things about all of our sets and the properties of the set. Is there anything that maybe people don't understand?
Yeah, so feel free to use the chat over on the upper right if you want to ask a question. And then McKenna is probably happy to answer those questions if you guys have any. Syntax, yeah, feel free. Syntax is on Twitch. If you have a question,
sure.
Feel free to go ahead.
Yeah, I'm looking at both.
Syntax says the definition for reals feels weird.
Yeah, so the reals is the union between rationals and irrationals. Sorry, I didn't know the symbol at the time. I just looked it up now. It's or like a capital I for the irrationals, but I didn't know the symbol for the irrational, so I just put irrationals.
Yeah, I
If
think
that
you're
makes
the.
more
Oh
sense.
gosh, that's really big.
Yeah, we haven't gone over what is irrational. Uh, hopefully you've done something about it in, I guess, like algebra. But basically, what is irrational is something that cannot be described using infinite decimal precision. Basically, or actually, no, sorry, no, it is sorry. Irrational is something that cannot be described using finite decimal precision. Also, if anyone's confused, the I is not imaginary. The I is supposed to be for the irrationals. Yeah, because the irrationals can only be defined using infinite decimal precision. I think it was. While the irrationals can be described using finite decimal precision. Is there any other?
The series
Let me check
definition for
the
the
math.
irrationals. Yeah, that's probably the. I feel like that's probably the determining factor, right? Does that help clarify a little bit syntax?
Oh wow, I should write R and N properly. I'm sorry guys, I don't have the cryptography that I need. If it makes if it makes better sense, I'm using a mouse, so it's harder for me. Maybe I'm just not the best math writer. Let's try. Let me try to copy. Okay, that's awful. Yeah, guys. Yeah, this dude can't see any sort of intense scrutiny. Uh, we're not really defining R as. It's more like we're just trying to get them comfortable with the sets we're going to use. Should I go into the next slide or is there any more questions? I'm gonna check your chat. Looks fine to me, I think.
Yeah, I think you're right, syntax. It doesn't feel quite as natural as some of the other sets, because a little bit more care is needed to, I guess, ensure that you have kind of some of these completeness properties that you need.
All right. What is a union intersection? Of course, we briefly talked about this before, but I think it's important to, I guess, get some intuition of what a union and what an intersection is. So as I said before, a union, in simple terms, combines sets. An intersection finds elements of sets that are the same. So in the graphic, well, yeah, in the graphic we can see that the intersection is where both of these sets meet, which is the elements that both these sets share. So maybe this is set A, this is set B, and they both share subset C. And we can write this as a union, or sorry, not sorry, intersection of B is equal to C. And then on the right, we can see a union. A union just combines two sets entirely. So we can say set A, set B, and then this whole is set C. Say that a union B is equal to C. At least for me, I like to like think of unions and intersections in words. I mean, it makes it easier for me to remember what they are. But also, just I feel like this graphic can help uh, with remembering what intersections and what unions do. And then I had some, well, uh, after some advice from one of my friends, they told me I should add the more formal definition of what a union and what a intersection is. And then for our next slides, we have something on logical notation. So I added some of the logical notation that we can have for unions and intersections. So the formal definition of what a union is some X inside a union needs to be both contained in A and contained in B. So we can say that if some element X inside the union, the union must get, if, element X contained inside the union A union B is some element that is either in A or an element in B. While an intersection of A and B, that X component inside that intersection, it must be a component inside A and B. So it must qualify both an element inside A and an element inside B. And then some of the logic we can replace and or using these symbols, respectively, for and or. And then we just substitute them in here and here with and. Is the 4. And then on our actual PDF, here you can press for more information on logic. Wow, thanks guys. I know my mic sucks.
Chat's getting spicy on the microphone.
I know. Let me try my phone. Let's see if that's better.
Okay, is this any better? I'm talking on my phone. Maybe it is, maybe it isn't. Wow, okay. Thanks, guys. Is there anything you want me to repeat that you couldn't hear because of my shitty microphone? Your chat. Everyone says this sounds better. Okay, that's good. Okay, 10 Center. It is your turn. You got statements.
Sweet. Okay, let's pop in over here.
Or if anyone wanted to ask any questions before. Infinitely better. Thanks, guys. I'll use my phone from now on.
Yeah, so welcome in.
Our definition of irrational.
Let's see, who is... So better yet saying bringing flashbacks from discrete math. Yeah, totally, right? And welcome in.
Oh, yes, discrete math.
We'll talk a little bit about linear algebra a bit later if you'd like. So I want to kind of take up kind of where we left off and chat a little bit about statements. So I just want to kind of generally say that a statement is a sentence. Typically, we're just going to go with a mathematical sentence here that's either true or false. We just want to make sure it's not both. So for example, something like 3 is bigger than 5. that is certainly a false mathematical statement or a false sentence, so we can deem this as a mathematical statement. If we have something like the absolute value of 3 plus minus 1 is less than or equal to the absolute value of 3 plus the absolute value of negative 1, if you've seen the triangle inequality, we know that's a true mathematical statement. And then we get into some of these kind of ambiguous cases like this, where like maybe x is equal to 5. So this could be conditional on our value of x. Or we get into these other kinds of statements like if x was 5, then x plus 3 would be 8, which right now feels kind of intuitively true, but we want to develop some kind of framework or procedure to be able to prove that this kind of statement is true. So probably the way that things are going to be laid out a lot in the presentations for real analysis is we're going to be thinking a little bit about a definition, and then we're going to be maybe giving some examples of that definition, and then moving into some properties, and usually those are called theorems with regards to the definitions that we're looking at. So McKenna talked a little bit about sets. Let's just define a definition here. We'll say that A and B are equivalent as sets, and we could write A is equal to B as sets. And let's say that's true, provided that A is contained in B, so A is a subset of B, and B is contained in A, so B is a subset of A. Is the plural of lemma lemmas or lemmae? I think it's lemmas. I think it's lemmas. So as an example here, if I have two sets, I'm going to call them capital A and capital B. Set A is 1, 2, 3, just contains these three natural numbers. Set B also contains 1, 2, 3. Then we could say that A is equivalent to B as sets. They're equal to each other. Because certainly all of the values inside of A, like A is literally a subset of B. They're the exact same set. And B literally is a subset of A. But let's take a look at something maybe a little bit more complicated. So let's say I have set capital A. This is the set of all natural numbers satisfying x squared is equal to 4. And what I want to try to do is I want to try to compare this to capital B, which is negative 2, positive 2, and capital C, which is positive 2. So which sets are equivalent in this particular example? Yeah, so Rex, your intuition wants to say B, right? But we've probably worked so much with like real numbers that it's actually A and C that are equivalent to each other. Yeah, so Darp's got it right. So A and C are what we're looking for here. All right, so even though it's true that negative 2 squared is 4, negative 2 is not contained as an element inside of set A, right? So B is not a subset of A because negative 2 is not inside A. Only positive 2 is. Right, because we're working with specifically the set of x's that are natural numbers, so they all have to be positive. So let's take a look at how we might utilize some of these ideas to actually prove a theorem with regards to sets. So let's say that I have three sets, capital A, B, and C. And I want to show that capital A union B intersects C is actually equivalent as a set to A union B intersect with A union C. So how would I start this and how would I set this up? Well, what we want to try to do, or usually we want to try to do with sets, is we want to try to start with thinking about an element on one side of the equation and seeing if I can kind of manipulate using some of the definitions and see if that element is also inside the set that's on like the other side of the equation. So in other words, we're going to basically just try to do this by definition. So the definition says these two sets would be equivalent if they're subsets of each other. So that's kind of the idea. So we're going to break the proof up into two pieces. We're going to start by saying, okay, maybe if I could show that the left-hand side was a subset of the right-hand side, that's step one. and I could show that the right-hand side was a subset of the left-hand side, then I'd be in business. So let's first try to show that the left-hand side is a subset of the right-hand side. So what we're going to do is we're going to assume that we take an element from the set that's on the left-hand side. Right? So we're going to take an element inside of A union B intersects C. And then we want to kind of figure out what that means. So based on some of the slides that McKenna provided for us earlier, we know that if X is in A union B intersects C, that means that X is either in A, or it could be that X is in B intersects C. It's got to be in one or the other of these sets in order to be in the union of these two sets. So I'm going to just do some stuff here so that you guys can see this a little bit easier. So let's pop this off, and I'll pop that off for a second so you guys can see that in Discord a bit easier. So basically now we've kind of broken down the first part of this proof into two cases. Let's kind of see what happens if X is in set A. What happens if X is in set A? Well, if X was in set A, maybe you would agree with me that X would also have to be in the union of A and B. Right? And if you agree with me that X is in A, then maybe you would agree with me that X would also be in the union of A and C. And if that's the case, then we could probably say that X is inside the intersection of these two particular sets. Great. So what do we know? We know that if X is inside set A, then it should land inside the right-hand set, which is A union B intersect A union C. Fantastic. But that was just one part of this case. So now we got to move into the other part. What if X was actually inside the intersection of B and C? What could we say over there? So what does intersection mean? Well, intersection means that X has to be in B and X has to be in C. It's got to be in both. So if X is in B and it's in C, then again we can kind of expand out a little bit, and we could probably say that X would have to be in A union B and A union C, or it could be, right? I could add A in there, and it's not really going to affect the fact that X has to be in B and C. And if that's the case, now I can convert that kind of sentence into a statement about the set. So I'm converting X in A union B and X in A union C into an intersection. Again, just trying to kind of capture the information about this set over on the right-hand side. So that's kind of the idea here. We're kind of starting with the left-hand side. We're going to try to break this down using some of our definitions. And it just turns out that no matter which case we choose from the left-hand side, we should end up getting X being a member of that set that's on the right-hand side. So we've proven our first subset for the overall theorem. So that's kind of the idea with these set equivalences. We can do this in the other direction as well. When I thought through this one, it was a little bit trickier, but if we start with the right-hand side and try to show that it's a subset of the left-hand side, we want to break apart the intersection definition and say that X has to be inside of the union of A and B and the union of A and C. And then when I was working through cases, I thought it was easier to prove this with X is in A or X is not in A. So we're going to look at two cases here and figure out what happens if X is in A and figure out what happens if X is not in A, because that should satisfy our universal set. In other words, we'll capture all of the elements by making these two particular cases. So I'm just going to pause here for a second. So MQ is saying, so we have X belongs to A, X belongs to B and C. We don't have other cases like X belongs to neither. Oh, I see. I think I understand what you're asking. So I think I understand what you're asking. So in the first part of this proof, so the first half, we're assuming that X is in one of these two sets. It either has to be in A or it has to be in B intersect C. So the only elements that we're working with are the ones that are either in A or the ones that are in B intersect C. And as soon as I figure out where all those elements live, and ideally I want to show that all of those elements live in the right-hand side, then we're done. Does that help clarify your question, MQ? I think that's what you're asking about. So you're saying we can use the left-hand side as sort of a collection. Yeah, exactly. So we know kind of, we're using the left-hand side to figure out where our elements X live, and then we're showing that those elements have to also live inside the right-hand side. Yeah. Yeah, exactly. And Kirby, yes, you're right. So all we're doing right now is just showing that these are subsets of each other, and I'm just trying to kind of outline what that proof might look like. So for kind of the second half of the proof here, we take the right-hand side, which is an intersection now, and we break this up into two cases, right? So either X is living inside of A union B, or X is living inside of A union C. But notice that in either case, like X has to be in A, right? Right? Either X is in A union B or X is in A union C. So, well, actually that's not true. It doesn't have to live in A. But let's take a look at all of the elements that do live inside of A first. And then we'll take a look at all the elements that live outside of A. Okay, so let's assume that X does live inside of A. And we also know a little bit more about where X lives. Like X has to live inside these two unions as well. But in this particular case, that doesn't matter, because what are we trying to show? We're trying to show that this X lives inside of A union B intersects C. So if X is in A, it already satisfies A union B intersects C, so we don't really have to do too much. It already lives in here. Cool. So now let's take one of these X's from the right-hand side and assume that it's not in A, right? So it's in one of these other sets, like B or C or an intersection or something like that. So all of the X's that aren't in A, but live inside this right-hand side, where do they go? Well, if X isn't in A, but we know that it lives in this right-hand side, specifically looking at this first one, I know that X has to be inside of A union B. But if X is not in A, and X is in A union B, I guess that means that X has to be in B for that to make sense. And we can conclude something similar about A union C. So if X is not in A, but we know X has to live in A union C, that's going to force X to be in C. So if X is not in A, we can kind of convert this statement about the right-hand side into X having to live in B and X having to live in C. And we know that we can rewrite that as an intersection of B and C. And that's going to pretty much clean up the proof for us, because now we know if X is not in A, we know that X has to be in the intersection, which means it has to be a member of this left-hand side as well. It has to live over there. So in either case, we get that members from the right-hand side must live in the set on the left-hand side. So we have that subset equality that we want as well. So we can conclude, since we have both of these subset containments, that these two sets have to be equal as sets. So I'm just going to pause here for a second. If you want to ask some questions about the setup of the proof, we can do that. The key takeaway that I want you to see here is, if we're working with sets and we want to show that sets are equal to each other, we usually start with an element in one side, show that it is contained in the other side, and then kind of vice versa. So I see Harl is asking, but isn't it an implication if X is an element of A union B? So let's pop back to, so if X is an element of A union B, it implies X is an element of A or B. So if X is in the union of A and B, then X could be in A, or it could not be in A. Could be in one or the other. And maybe I can show this a little bit better with a picture. So let's grab these two statements, for example, and I'm just going to pop over into OneNote. No sponsors? No sponsors today, unfortunately. So here's what we know about the right-hand side set. So the right-hand side set that X has to live in both of these. Right, so I have some information about A and B, let's say. So A and B. I know that X has to live in the union of A and B, which would look like this. So either X could be inside of A like this, or it could be outside of A. I don't really know. Right, so maybe I'll kind of shade in. So like X could live in here, or it could live in, it could live over here. One or the other. And the same thing kind of happens over here with the union of A and C as well, right? So if I have A and C, I could say that X either lives inside of A, or X could live outside of A. It's got to be one or the other. Why can't we just use set theory diagrams to prove everything? I'm not going to stop you. Yeah, Riz is correct in the sense that it's going to get really tricky when you have more than just a couple sets. And sometimes in analysis, we do have to use infinite intersections or infinite unions of sets as well. So things can get a little tricky. And I think that's a good answer to your particular question, Kirby. But for these smaller examples, I think it's really helpful to be able to draw these diagrams and kind of see where things live. Life sucks when you have a huge union or intersection symbol. Yes. Uncle Talks on Twitch is saying, so in general, we just need to show that an element from the sets are also within the other sets. Yeah, exactly. And you're kind of using those definitions, right? So those definitions that McKenna gave us of what does union mean, what does intersection mean. Yeah, exactly. So we're using those definitions to try to get the work done in these particular theorems. So this is just kind of a little bit of a slide about terminology. Most of you that have taken some math classes probably know a little bit about terminology, but we'll use kind of theorems, axioms, lemmas, corollaries quite often. So it's helpful here just to have kind of a general idea of what that means. So if one of our presenters, for example, I think Dingus is going to talk a little bit about the axiom of choice. That's an axiom. So that's a kind of a foundational item. We just kind of believe that that's true. We're not going to prove that thing. We're going to build off of that axiom typically to do other mathematical things. Euclid's Elements is another place to go for some famous axioms in geometry, for example. A lemma, typically I use this for like a technical result, like a very technical result, and usually something that I would use to help prove a theorem. And a corollary is just going to be a result that typically follows directly from a theorem. And you don't usually have to do a lot of kind of technical proof writing here. It's usually fairly straightforward with just a couple lines of proof. So as an example of a corollary, if we take that last theorem that says that these two particular sets are equal, a corollary to this particular theorem might be if I have two sets called A and B, then A intersect B union A intersect not B is equivalent to A. And I've outlined just a little bit of a proof here at the bottom. So according to the theorem, we can take that first statement, A intersect B union A intersect not B. We can rewrite that using the theorem that we just proved as A intersect B union not B. And of course, B union not B is the universal set. So A intersect the universal set will just be A. All right, so that's what we mean by a corollary. It kind of follows pretty quickly from the theorem that was just proved before it. So what's Uncle saying? Is there a particular proof method preferred for proving set proofs, such as direct contradiction? It probably depends on the kinds of sets you're working with. So right now I've kind of outlined what I would call a direct proof. So we're basically just proving using the definition. That's a pretty standard approach for showing that sets are equal. Although contradiction, I have seen contradiction used as well. So you can kind of assume that something is not true and then maybe make your way through to a contradiction. But we'll talk a little bit more about contradiction and contrapositive the next time that I get together with you guys. And hopefully have some good examples then. Can we derive second order logic in lecture 2? I don't even know what that means. Do you want to do that? Oh, you're welcome. You're welcome, Uncle. No worries, no worries. Oh God, no. I've actually never taken like a secondary course in logic. It all looked a little too scary for me. You can always have fun in my lectures. I don't mind. So now we really want to kind of move into what I would consider kind of the nuts and bolts of what we want to get to. It's like we have these conditional statements in mathematics, and they come in the form typically that look like this. It looks like if some statement, then some other statement. And we want to try to figure out how to prove these things, right? And set up a process for how to deal with these kinds of statements. I'm going to refer to P as the hypothesis of the statement, and then I'm going to refer to Q as the conclusion of the statement. So if, for example, we go back to one of the conditional statements we saw earlier, if x is 5, then x plus 3 is 8, I would consider the hypothesis to be x is equal to 5. That's the statement that comes after the if part of the conditional statement. And I would consider the conclusion to be x plus 3 is equal to 8. Here's another example. If a real number epsilon is bigger than 0, then there exists a real number delta bigger than 0, satisfying epsilon times delta is equal to 1. So in this particular case, we might say that the hypothesis is epsilon is bigger than 0, and in addition to this, epsilon is forced to be a real number. And we might say that the conclusion is that there exists, right? There's an existence of this real number delta that's positive, satisfying epsilon delta is equal to 1. Okay, so there's this special delta that has this particular property of interest that we're looking for. Now, conditional statements can get really, really tricky, especially when we start using phrases like there exists and for all. And we do tend to run into a lot of those in real analysis. So I want to take a lot of time after kind of the standard approach here to look at quantifiers and look at how we do proofs with quantifiers. So if I just have a blanket conditional statement and I just want to show that it's true using the standard approach, we're just going to assume that the hypothesis part of the conditional statement is true. We're going to try to use some logical statements to move from the hypothesis to the conclusion. And once I connect the hypothesis to the conclusion via some kind of sequence of truthful statements, then we know that the overall conditional statement must be true. Jeff in Twitch is saying, notice that for all epsilon there exists delta. It means that delta is a function of epsilon and differs from there exists delta for all epsilon. Yes, yeah, so we might play around with that a little bit in the next lecture. I like that you're heckling. So let's take a look at, what a standard approach proof might look like. So here's our conditional statement. Intuitively, we think it's true. So how do I prove that? Well, the proof would go something like this. Let's assume that x is 5. And then we need to do some logical construction to get to x plus 3 is 8. So it seems reasonable here maybe to add 3 to both sides. And then we can simplify the right-hand side using field axioms or something like this if you want to get super technical with me. But let's just say we know that 5 plus 3 is 8. So we've reached our conclusion that x plus 3 is 8. Cool. So we assume the hypothesis. We try to give a pathway to the conclusion. And once we get to the conclusion, we know we're done. Now, how do we deal with more complicated conditional statements? Because that's really the crux of what we're doing. Oh, this is a cool question. So Rex asked a really cool question. Can I do it backwards? What say you, chat? Can we start with the conclusion and work our way to the hypothesis? I think that's a good question. Those of you that have taken more formal logic will know the answer to this. So Kirby says, if it is an if and only if. Uncle Talk says, I think yes. So my kind of like words of advice for this particular example is to just kind of notice you still need to kind of classify what the hypothesis is and what the conclusion is. So I think this is a really nice thing to talk about. So I want to take a moment to just kind of to talk about this, because this question does come up quite a bit when I teach proofs. And there's a little bit more kind of foundational logic here too. But the question is this: can I start with the ending statement, which is x plus 3 is equal to 8? And then I'm going to be like, oh, well, what I could do is I could just subtract 3 from both sides. Okay, cool. That gives me x is equal to 5. Sweet. I'm done. So my logical math brain says, you've done the required thinking and the required work to help you set up the proof, but you technically actually haven't proven it. So working backwards is fine, but I would always consider this rough work. The proof has to start with x is equal to 5 and kind of lead me in the direction of the conclusion. That's what this is telling me, right? This is telling me start with x equals 5. This is my start. And this is where I need to get to. The path of math rebels. So I don't know if that's helpful. I think it is helpful to sometimes think about the concluding statement and ask yourself, how could I get back to the starting statement? I think that's a very valid question to ask. But when we go to write the proof, we always start with our assumptions, which is, in this case, x is 5, and then we need to move forwards to get to the ending. If this was an if and only if, then we have a little bit of chance to play around a bit more with that structure. Right, so Uncle is saying you can't go backwards in writing the proof. Correct. So for that particular proof, we want to start with x equals 5 and then get to x plus 3 is 8. Because this conditional statement is truthful only when we assume that x is 5 and can show that we get to x plus 3 is 8. If that makes sense. That's what this statement is saying. And in some sense, to be completely fair, the work that we've done here would prove that if x plus 3 is equal to 8, then x is equal to 5. So there's a big distinction between these two statements, right? One is telling me start with x is 5, end with x plus 3 is 8. The one that I just wrote down in red says start with x plus 3 is 8 and show me that we can get to x equals 5. Yeah, of course, this particular statement that we have is an if and only if. It's provable in both directions, but the way that we stated it here gives the very clearly defined starting and ending point. All right, so this is kind of where we want to build ourselves up to. We want to build ourselves up to being able to work with quantifiers. So here's another example. If a real number, epsilon, is bigger than 0, then there exists a real number, delta, bigger than 0, satisfying that when we multiply these two numbers together, we get the number 1. Now, if we kind of start out with our standard approach, we're going to assume the hypothesis. So we'll assume that we have a real number, epsilon, that's bigger than 0. And we want to get to the existence of a delta that's positive, satisfying epsilon delta is 1. That's where we want to get to. But how do we do that? Like, how do I get there? Right? And it does take a little bit of mathematical nuance to be able to kind of work with some of these things. So this is a good time for us to kind of switch away from the standard approach a little bit to talk about quantifiers. So there's two main types of quantifiers that we need for real analysis, and you're going to start seeing them next week when Sir Dingus starts with kind of the main lecture from real analysis, right? When we talk about numerical sequences. So we have universal quantifiers. This is a way for us to describe a property that holds for everything, every element inside the set that we're working with. So we have a universal quantifier. And then we have existential quantifiers. This is a way to describe a property that holds for at least one member. So one or more, but not all. So a couple examples. And maybe you can tell me if you believe they are true or not. Every real number larger than 1 is positive. Do we think that's true or false? True or false? You can appeal to your intuition here. You don't need to prove anything for me, but it feels true, right? It feels true. Yeah, I think most of you are okay with that. So every real number bigger than 1 is positive. How could you prove that to somebody? Right, so what would we have to do? Levy, yeah, sure. After the lecture is over, I'll have some time to talk about some stuff for sure. D. We're going to chat about quantifiers. I'm going to show you a couple quantifier proofs, and that's it for the lesson for today. So it's probably within the next 20-ish minutes we'll be done. So the idea here is we have this is called a universal quantifier. It's saying every one of these numbers, right? Every one of these numbers bigger than 1 is positive. So we're specifically looking at all of these real numbers that are strictly bigger than 1, right? Or maybe on the number line we have something like this. Now, kind of theoretically, what we would have to do is we'd have to actually dive in and check all of these numbers, right? So maybe I pick 2. 2 is bigger than 1. Is it positive? Yeah. I could pick another number up here, I don't know, 3.14. That's positive, right? And that's bigger than 1, that's positive. There's a number up here, favorite number, best prime, 17. Bigger than 1 seems positive. So the idea with universal quantifiers is we kind of have to look at all of the elements inside of a set, and the particular set that we're working with are the set of real numbers such that x is bigger than 1. So we're looking at all of the members of this set and checking to see if they are positive. And that happens to be true. Okay, let's take a look at secondary example. How do you feel about this one? And again, just appealing to kind of your intuition about how we talk about coordinate pairs here, not being super specific about how they're defined or anything like that. So we have an ordered pair, let's say in the xy plane, such that x squared plus y squared is 1, right? And we're working in of course, the typical Cartesian plane. So x and y are real numbers here. So is it true that there exists an element in S, right? So is there an ordered pair in S for which the x coordinate is 0? Is that true? Amen says false. Oh, wait. Rex thinks true. We got Harl, Darp, Cracked thinking probably true. Yeah, so we could actually probably construct a specific point, right? So if this is the property that we would like it to satisfy, x squared plus y squared is equal to 1, we could actually just force x equals 0. Right, so we get 0 plus y squared is 1. And then if we apply the square root to both sides, then we get the root of plus or minus 1, which should be plus or minus 1. I don't know why I wrote it as root plus or minus 1, but okay, we should be good to go there. So there's actually maybe two candidates. We would just have to check and make sure that they fit inside of set S. So we have 0, 1, and 0, minus 1. So all we have to do now is say, okay, do these belong in the set? Yeah, they feel like they belong in this set. X and y are both real numbers, and we know that these values of x and y satisfy x squared plus y squared is 1. So there we go. We've shown the existence of an element. We just had to find it. For example, 0 and 1. I found it. There it is. Found it. So notice how that feels a little different from back here, right? Every real number. I had to actually literally think about all of these real numbers. Every single one of them. All uncountably infinite many real numbers to figure out if this was a truthful statement. What did we do down here? There exists. All I really had to do was build one, right? I had to build or construct, I'm going to call it construct, a element that actually had this property that we wanted. Right, so something about these quantifiers feels different, right? Like we approach them slightly differently depending on what kind of quantifier they are. Okay, let's do a couple more examples. Make sure you get the idea. What do you think about this one? All prime numbers are odd. Also, Uncle, this is hilarious. Twitch is not allowing you to say the word square. That's so funny. Yeah, okay, cool. So Rex has given the number 2. What do you mean? So Rex has just said 2. What does that mean? What do you mean, Rex? Hi, Victor. Welcome on in. Yeah, Darp. There you go. So Darp's got it. Yeah, okay, perfect. Rex, you got it. Nice. So this says all prime numbers have to have this property of being odd, right? All prime numbers. Well, 2 is what we call a counterexample. Two is prime and even, right? 2 is a prime number that is even. So this particular mathematical statement is false, right? Because 2 is prime and even. Hi, Doom. Welcome in. Yeah, it's a pretty chill stream today. 57 is also prime and even. How dare you? And what's our takeaway here? Our takeaway is we started with what kind of quantifier? We started with a universal statement about prime numbers, right? And what did we do? To disprove this, to kind of convince ourselves that this was false, we found a single counterexample. Okay, so to disprove a universal statement about a set, all you need to do is find one element from that set that is a counterexample to that statement, right? And that will kind of prove the falseness of that statement. Okay, last one. Do you think there is an integer solution to the equation 2x plus 1 times 3x plus 1 is equal to 0, with, usual standard operations for algebra here. Can't believe 13 is composite. Damn. I hate to inform you that we live in a world where 91 is not prime. Oh my gosh, mind blown. What are the solutions to this equation, by the way? Yeah, so Levy, you got it. So yeah, we have x. So these are the x in the reals, I guess, such that we have x is equal to, oops, never mind. Let's just write it down. It's just two numbers. It's -1/2 and -1/3. Okay, here's our solution set. So we can kind of go through each one of these elements inside the solution set. We can check to see if they satisfy the property of being an integer. Right, so we're kind of looking through each one of these and going, not an integer, not an integer. And after we're kind of done checking all of these potential solutions, then we can make a statement about what's going on. So we believe this is false. And I want you to just kind of, again, take a step back and figure out, how did we realize that this was false? We actually developed a solution set. We looked at every single element inside the solution set, and we showed that none of those things have the property of being an integer. Okay, what kind of quantifier did we have? We had an existential quantifier, right? We had there is, or there exists, an integer solution, right? An existential quantifier. To prove that it was false, I had to go through systematically every single element inside this set and make sure none of them were integers. All right, so let's summarize. Brute force, ultimate doom, you got it. Exactly correct. Brute force method. So, if I'm working with universal quantifiers and I want to show that that statement is true, I have to actually go through and check every single one of the elements in the set to see if they have the property I want. Right? Did all of the real numbers inside of this set have the property of being positive? Yes. Right? Therefore, this is a truthful statement. To show that a statement with a universal quantifier is false, we have to find at least one element in the set that doesn't have the property that I want. Are all prime numbers odd? No, because I can find one prime number that's even, the number 2. Is there another way other than brute force? Not that I know of. To show a statement with an existential quantifier is true, logically we want to find at least one element in the set with the desired property. We usually do that via construction, and we'll talk a bit more about that before I go. And then to show that a statement with an existential quantifier is false, we actually have to systematically go through every one of those elements in the set and show that they don't have the desired property. Okay, so now we should have enough firepower. Actually, we'll stop here for a second and see if anybody has any questions before I press on to the last segment of the course. Uncle is asking, any suggestions for problems from the real analysis books we would recommend? Yeah, I'm going to post some recommended problems for us in the mathematics server after our lesson today. So probably by tonight we'll have those up for you guys, for sure. Yeah, so this is kind of like the idea here is to do like a real analysis course, really focusing on calculus concepts. And the reason I wanted to spend a significant amount of time on proofs is because we're going to be doing a lot of proofs 1, and a lot of the proofs that you're going to see Dingus do next week are probably going to involve quantifiers. So let's come back to this previous example. A real number epsilon bigger than 0 is our assumption. We want to show that there exists a real number delta satisfying a property, right? I want to show that there exists a real number. How do I show the existence of this number? The easiest way to do that is to construct it and ensure that it satisfies the property that we want. I want epsilon delta to be 1. So couldn't I just take that equation, divide both sides by epsilon? I should be able to divide by epsilon because epsilon is bigger than 0, so I don't run into a division by 0 problem. Is delta going to be positive? Well, delta should be positive because epsilon is positive, so we should be okay there. So there we go. Now we know how to construct delta to make this work. Oh my gosh, we have a raid coming in. Javakma, thank you very much for the raid. Oh my gosh, how is your stream? Welcome in, raiders. We're doing a little bit of proofs today. Raidva, I love that. That's cute. Oh my gosh, is that a kingdom key? So cute. We got a raid on Twitch, Darp. Sorry, give us a second here. Yeah, we're doing some analysis, some intro to analysis. A kingdom key, yeah, that's what I thought. It reminded me of Kingdom Hearts. Okay, so let's finish off this example. We've constructed the delta that we want, so now we can come back and actually prove the thing. Remember, the standard approach is to start with the assumption and try to logically get to the conclusion. So we're going to assume that we have this real number epsilon that's bigger than 0, right? We can assume that we have that. That's an assumption of this particular statement. Now, we move into what I call the construction step. We've already constructed what delta has to look like in our rough work on the last slide. I know that delta has to be 1 over epsilon. So now I'm going to introduce that to the reader. I'm going to say, hey, well, why don't you just consider this delta, right? This delta is 1 over epsilon. And then I'm going to convince the reader that this is the delta that they want. Right? I know that delta is bigger than 0 because epsilon's bigger than 0. And I know that if I multiply both sides by epsilon, I get epsilon times delta is 1. Therefore, I get to my conclusion. There exists a real number delta. I know exactly what it looks like. It's 1 over epsilon that satisfies the properties that we want. It was a good stream? Fantastic. Yeah, thanks, Raiders. My name is Pen Center, by the way. I'm a math streamer. Math and Zelda streamer by trade. We're just over on Discord right now in the Mathematics Mandelbrot server doing some intro for our real analysis course that we're firing up next week. That's the proof. Yeah. So notice what we did, though, right? What we did back here was we said, okay, dang, this is an existential quantifier. I have to show that this thing exists. So I'm going to go to my property, which is epsilon delta is 1, and I'm going to construct that thing. Okay, so all of this is the rough work. I'm constructing the thing that I want to use in my proof. When I actually write out the proof, I don't show how I construct this thing. I just know that I've done that in my rough work. I call this the construction step. So you'll see this a lot when you go to read the books. They're like, just consider this particular value of blah, blah, blah. And then you're like, what? You're like, how did you get that? Yeah, and Aha saying, have you tried guessing and checking? Well, we don't want to really guess and check, right? We want to actually... It's more helpful, I think, if we do a little bit of rough work on the side and kind of construct the thing that we want, and that way we know it satisfies the properties that we want. So I hope you're just trolling. But I mean, this one we could guess and check pretty easily, right? I know that multiplying these fractions together gives me 1. But it does get a little bit trickier with the analysis part. And you'll see that coming up here over the next couple weeks. But that's the general idea. I want to construct something, and then I want to convince the reader that it has the properties that we want. Thank you very much for the kind words, Doom. That's much appreciated. Okay, so let's round this out with another construction method. We'll do a construction method and a choose method for proofs here. So let's kind of more formally define a function. So let's say I have 2 sets, and I'm going to define this map from A to B. We're going to call it a function. So it should satisfy all the nice kind of properties that we expect a function to satisfy. Okay, so it's well defined, and it's going to map all of the elements from A into set B somehow. Okay, so we're going to assume it's a nice function. Let's say that f is injective, or 1-to-1, if for every x and y in A, I have that f of x equals f of y implies x is equal to y. Okay, so I'm introducing a new notation here. This upside down A is a universal quantifier. So this says for every x and y, right? So for all elements in A, basically, right? Any kind of, I choose two elements from A, this implication has to be true. So f of x equals f of y has to lead me to x is equal to y. So that means injective. And f is surjective or onto if for all b in B, right? So a universal quantifier. So for every element in B, there exists an element in A satisfying B is equivalent to f evaluated at A. And then, of course, if f satisfies both of these properties, we call it bijective, or sometimes I've heard that called one-to-one and onto. So lots of quantifiers in here, right? I see a couple universal quantifiers and an existential quantifier. So maybe helpful here to take a look at some examples. So yeah, exactly. I think it's not, let's take a step back here to kind of think about a function. Let's think about x squared, right? Everyone knows kind of what x squared looks like. And I'm going to claim that x squared under this particular map is one-to-one, but not onto. Yeah, Zach, if you want to drop some, you can drop some links to the elements if you want into chat there. So let's break this down a touch. Maybe we can find a counterexample to this showing why it's not onto. Because I think this is a good example, right? So my function f is a map from the natural numbers to the natural numbers. How do I know it's not onto? How do I know it's not onto? So onto means every element in this n has to come from an element over here. Can you find an element in this n where I wouldn't be able to take an element from the first n and map it over there? Yeah, Darp, you got it. Yep, not all natural numbers are squares. Perfect. So Ultimate Doom, I want you to hold on to that for a second. PYG, yes, you got a good one. PYG, hold on to your example, Doom. I think that's a good one coming up. So yeah, let's pick 3, for example, right? Let's pick 3, right? So 3 is inside this set n, right? But can I find a number over here that maps to 3? So can I find an f of a, let's say, that's going to equal 3? Well, we know that f of a is a squared. So if I'm just working with this particular equation, when I take square roots, I would get plus or minus square root 3. And this particular number is not a natural number, right? Not in n. So there's no natural number that gets mapped to 3. So this particular function can't be onto. Let me know if that makes sense. Yeah, Jeva, you got it. Yeah. So it can't be onto. Because we're fussing around a little bit with the sets we're working with, that's why it's kind of funky. What about this one? What if we play around with the domain and codomain a little bit? What if I change the domain and codomain a bit? So what if I change it to now be able to work on any real number as input, and my outputs land from 0 to positive infinity, right? 0 inclusive. So I'm going to claim that this is onto, but not one-to-one. And I think Ultimate, you probably have what we need for this one. So why is it not one-to-one? So remember, 1-to-1 means that if I take any two inputs, any two outputs any two outputs from different inputs, this has to imply that those two inputs are equal to each other. Uncle, exactly. So onto means it has to map onto that set on the right side, exactly. And Jeva, yeah, you got it. Any negative input, any negative input has output, but it might not be a 1-to-1 output in this particular case, right? So I could, for example, say that f at -2, by definition, that's -2 squared, and that's 4, okay? So negative inputs are okay. It's going to land in this set, so that's fine. But what if I do f at 2? F at 2 is 2 squared, which is also 4, right? So what have I shown? I've shown that there are two values that map to the same number. So it cannot be 1-to-1, right? It doesn't satisfy, so this isn't satisfied. Right? I found two numbers that map to the same output. 4 is equal to 4. Right? So f at -2 is certainly equal to f at 2, right? But it's not the case that -2 is equal to +2. Right? So we found a counterexample. When a mapping isn't 1-to-1, you lose information. Yeah, possibly. Possibly. 1-to-oneness is super nice because you can define inverses, for example, relatively straightforwardly without having to worry about branches and things like that. Okay, and last one, of course, if I play around again with these domain and codomain, then I create a function that's neither 1-to-1 nor onto. But I won't go ahead and prove that. I'll let you kind of think about that on your own. So I want to do just a couple, another quick construction method here with regards to functions. So let's prove that this particular function is onto, right? So starting in R, my output space is 0 to infinity, and my rule is x squared. How do I prove that this is onto? Well, this is a standard approach proof. We're going to assume that we have a function, right, from R into this particular set with this particular rule. So we can make that assumption. We know f here is a function. Let's also assume that f is a function. Now, to show that f is onto, we want to go to the definition. The definition says, for any b inside of this set, I have to be able to find an a satisfying b is equal to f evaluated at a. Right? So for any b, I have to be able to find an a that has this property. So what do? We got to construct a. We have to figure out what does a look like based on the specs that are given to us. Okay, so we have to construct an a in the real numbers satisfying this property. Okay, so I'm going to say let's just take something from b and let's consider a is equal to the square root of b. This is my construction step. I kind of constructed this mentally before starting my proof. And then I'm going to show the reader that f evaluated at a is really just root b squared. Right? And when we square that, we should get b, right? So I found a particular a that gets mapped to b. Okay, this a is a real number, right? The square root of this a should be okay. Do I need to be a little bit careful about, let's see, oh no, b, okay, sorry. So I know that b is a positive number, so I can apply this square root and it should be okay. Okay, so a should exist because of the positive or zero-ness of b, right? So this a should be okay. I was worried a little bit about maybe negative b's, or maybe that a might come out to be negative and that would fuss some stuff around, but this should be okay. Okay, so the kind of key idea here is I've constructed an a that should satisfy the properties that I want, therefore I know f is onto. Peak and Flow, welcome in. Does this relate to the vertical line test? So 1-to-oneness would relate to the horizontal line test, I think, and then vertical line test would be for functions, if I remember correctly. Okay, so I just wanted to give you kind of another example of where we might use construction when working with functions. There's another proof here. I call this the choose method. So when we're working with, universal quantifiers inside of our conditional statement, sometimes we want to actually choose the thing that we're working with and show that things are true. So I'll just kind of quickly outline what the choose method might look like. So if I want to show that this particular function is 1-to-1, which I suspect is true, to show that f is 1-to-1, I have to show that for all x and y in n, then this implication is satisfied. So how do I work with the universal quantifier? I'm going to select a representative here, so representatives x and y, and then I'm going to go ahead and try to see if the implication is true. Okay, so I call this the choose method because we're actually going to choose x and y inside this first set, so I call it the choose step, and then I have to show this implication is true. This is an implication, so I assume the hypothesis and see where that goes. So if f of x is equal to f of y, then I can just apply the rule. That means x squared is equal to y squared. I can take square roots. That gives me x is equal to plus or minus y. But y has to be in n, right? So I've chosen y to be in the set of natural numbers. So one of these doesn't work, right? Maybe if we assume that x and y are positive because they're inside of n, then negative y can't be inside of n. So that gives me a single solution, x is equal to y. So I've shown the implication that I want. I've chosen the numbers from the set. I've assumed the hypothesis that f of x is equal to f of y. And I've used that information to get to x is equal to y, right? A single solution. So we know that f is 1-to-1. So in summary, if a conditional statement contains an existential quantifier in your standard approach, construct the representative that you want and then show your audience that it satisfies the property. And second, if a conditional statement contains a universal quantifier in your standard approach in your forwards direction, you're going to choose a representative from the set and then show that it satisfies some desired property. So that's really, I think, all that I have to say with regards to kind of some of the proofs that you're going to be seeing over the next little while. And McKenna and I think McKenna's still chill here, so we're happy to take some questions if you have them. Otherwise, we'll go ahead and we'll try to grab some kind of questions for you to try and post them into the forum in the mathematics server. So McKenna, I'll let you kind of jump on, and if there's anything else you want to add, you're more than welcome to do it.
I think unless anyone has any questions.
You're chill, sweet. Yeah, I'm chill too. So if there's any questions on Twitch or in Discord, feel free to let us know. And I guess for any of you that are kind of jumping in, this is kind of the style of the presentation, right? So you kind of make a little slide deck or like make some notes. Usually we'll take a little bit of time to help you review those notes so that you're not kind of jumping in blind and give you some recommendations with regard to those notes. So yeah, so if you're interested in kind of continuing in attending, you're more than welcome to do that. And if you're interested in presenting, let us know as well, and we can make sure you're set up to help us out.
Right.
So why does 2x plus 1, 3x plus 1 equals 0 only have two solutions? How dare. Oh, bless you.
Thank you.
You want a real answer, Aha? What axioms am I allowed to to use? Assuming that we're over like a nice field, then we can just set each of those equal to 0, right? Yeah, I will be back for the bonus math stream in a little bit, in about an hour or so. Yep. And then we have the linear algebra reading group coming up at 7 o'clock Pacific as well. So lots of math today. Lots of maths. Emac, thank you very much for the follow. All right, Dark, thanks for coming and hanging out. Levy, I'm going to stick around. I'm going to just jump off of Twitch right now so that we can kind of close Twitch off and then I can port that over to YouTube for us. So these lessons will always be ported over to YouTube after we're done. And I'll post that into the reading group category for you guys, just in case you had to leave early or came in late or something like that. Yeah, McKenna and I are Pacific time, so it's a little harder to juggle our times around. But future presenters, if we need to move some stuff around, just let us know. So I think we're presenting a little bit early next week, but I'm happy to present a little bit later on Saturdays and Sundays too. Like 7 o'clock tends to work really well for those of you that are over in like Eastern Asia, or sorry, Eastern Europe. Posted under Help University. Cool. All right, guys. So is anyone actually on? So Dawn's on. I'm going to set up a raid over to Dawn. So thanks for coming and hanging out with me. Let's get over into Dawn. It is a big Twitch math day today. Yes. So take care, everybody, on Twitch. I'll be back in about an hour or so. And thank you very much for the raid, Jev. Thank you very much. Can we do a quick shout out? So if you haven't done so, please join Jev, fantastic streamer of all things gaming. And when you start streaming math, let us know and we'll add you to the Elements Discord community. All right, we're going to head over to see Dawn. Take care, guys. I'll see you in a little bit.